Hello, hello. Uh, Let me show this is example 3.7. So this was actually 3.5 and 3.6, and this is 3.7. Now, this Bismillah Rahmani Rahim, this is example 3.7 of the same book and the same topic we were discussing about that. And here the problem is very simple. Is that uh, if the problem that we have solved earlier, um, and we say that if the intersection of the curve intersect at a station 100 plus 0, we have to determine the stationing of PVC, PVT, and the curve high point. So, uh, if you use this curve length, we have determined earlier in that example. So, it's very simple that PVC is uh, PVI minus L by 2. So it is 96 plus 29.5. And PVT is what you need to do is to add L by 2 in the already PVI. So you will get this value. For the high point, because this is a crest curve, so it's very simple. The formula is given as uh, XHL is equal to K times G1. K is 247 and G1 is 1. So that's 247. Simple and uh, conventionally write 2 plus 47. And the station for this will be from the curve. This will simply you have to add uh, the PVC station plus 247. So it is the station is 98 plus 76.5. So this is a very simple example uh, that that is being solved. So let's go to another example that's 3.8, and let's see how it can be solved. Here we have been given a seg vertical curve, uh, 2.5 intersecting some grade, and we need to find that grade. Uh, the final grade is positive and low grade is elevation at 270 feet. And at the low, there is some low point. It's also given here. That is 141, has a station 141 and an elevation 270 feet. The PVT of the curve is at elevation 274 feet, but the station is not known. The design speed of the curve is 35 miles per hour. Determine the station and elevation of the PVC, X, and PVT. Now, this data is like this. G1 is given to us. G2 is not known to us. We have been given design file speed, and we have the elevation, the low point elevation. This station low point elevation is 270 feet, and it is at 141 feet. Or we can say this 14,100 feet from somewhere. Uh, so again, the elevation of PVT is given to us. First, in order to solve this problem, we start with solving the length along the curve. So let this length is known as K times A, and since we have been given 35 miles per hour speed, for 35 miles per hour, our K is 49. So we can say that, so so we can have length is 49 times A. But let's start with the basic. Like this, we know that the equation of the parabola is y is equal to ax square plus bx plus c. We also know a is equal to g2 minus g1 over 2l. And since we know that a, capital A, the length is, what I mean is the k times a that we were calculating a, it's the algebraic difference of the grade. So what we can do is to replace G2 minus G1 over 2, G2 minus G1 with this capital A. So we can, if we replace G2 minus G1 with capital A, and this 2 is already present and 100 is also present, so this small a becomes A over 200L. So we can write that L is equal to K times A, and since A is equal to A over 200K, so we can write that A is equal to 1 over 200K. Simple mathematics, right? We have substitute capital A with small a. Now, what we are going to do next is, from the very basic equation, we know that B is equal to G1 is equal to minus 0.025, and C is the elevation along the curve. The elevation is at the start of the curve. So for 30 miles per hour speed, table 3.36, we find K is equal to 49, and hence the length of the curve is 49 times A. Also, we know that the lowest point is K times G1. So this becomes X is simply 122.5 feet. Now, in this equation, we know X, we know A, we know B, the lowest point, and we don't know C, that is YPVC, but we say along some point on the curve where there is X, there is the lowest point, and whose elevation is given to us. So what we are going to do here is to use this value of X to know YPVC. So since X is 122.5, as we can found out from here, and A is simply 1 over 249 that we have found from this relation. And we know that elevation of the lowest point is 274, so we find elevation at the start of the curve is 271.53. Then what we are going to do next is, we know that PVC is, since X is known to you, so we can say that the PVC is simply 122.5 feet away. The station is 14100, and it is 122.5 feet from the start of the curve. That's why we can say the start of the curve is simply the station that has been given by X minus the distance of X from PVC. We find that this is 139 plus 77.5. It's very, so conversely, if I say this PVC is say 139 plus 77.5, and the station is 141, so that the distance is 122.5. That's how they have calculated the stationing of PVC. Now, for the length of the curve, we'll use this equation. Now, in the basic equation, we'll replace X with L because length of the curve is not known to us. So what we have done here is simply use this equation in which y is equal to al square plus bl plus c, and just equating, we know that the elevation at the start of the curve was 274, and this is no surprise. This should not be surprised because it's already given at this point. Because when we say x is equal to L, we means we are standing somewhere here. So that's why the PBT is given, and that's why when x is equal to L, this y value, the value of y at the end of the curve is simply 274. So what we have done here is we have substitute 274. We know A, we know B, and we know C. So by simply doing this exercise, we know the elevation of the PVI is 267.52. So this is how this problem is solved. I hope that I was able to communicate this problem.